Right? So the learning happens in the problems. Let's look at this particular problem. This is from the OpenStax book. Um, the question goes like this. We've got a hunter who's trying to tranquilize an elephant, maybe so he can put an RFID tracking tag on him, maybe for less savory purposes. So, what is the momentum of a charging elephant? Well, momentum is just the product of mass and velocity. So the momentum of the elephant will be equal to 2,000. So the elephant is a solid 2 metric tons. So the amount of momentum in the elephant's movement is what, 15,000 kilogram seconds. It's a very odd unit of measurement if you think about it. Oh, sorry, kilogram meter per second. Yeah, I was missing one. What I was meaning to say is that you could also write this as Newton seconds, uh, which makes sense because that's actually the form that we write down impulse in. So the dart that the hunter tries to shoot at the elephant is going a lot faster than the elephant, but is also a lot smaller. So the momentum of the dart is only 2.4. That's that's a lot smaller. The elephant is not even going to notice that. And then lastly, the momentum of the hunter as he runs bravely away. The hunter is 90 kilograms, running at a speed of 9.4. And what's that momentum? It doesn't matter because the elephant is faster and is going to catch him. So, RIP. Any questions about this sort of calculation here? Eric, yep, you are correct. I slipped a decimal point. Yep, still rip. Let's look at this from a slightly different point of view. Let's say that you've got one of those super bouncy balls and you drop it from a height of 1 meter. When it bounces back up to you, I can do a better drawing than that. when it bounces back up to you, it's only 0.8 meters. So the question here is, what impulse did the ground exert on the ball? So impulse, which remember is a vector quantity, so impulse is equal to the change in momentum. In fact, we usually say that impulse causes a change in momentum. What we would like to know then is, what is the velocity of the ball just before it hits the ground and just after it hits the ground. So we can say situation A is just before. Situation B is just after. So how do we calculate how fast the ball is going right before it hits the ground? Anyone have any ideas there? Maybe? Yes? No? Trainmaster, you've been quiet all day. Usually you've got a lot to say. What do you think? How do we go about calculating the velocity of the ball right before it hits the ground? Trainmaster, you're right. We do have the height, and the initial velocity is 0. So we can use kinematics, but energetics works too. So just because we're in the momentum chapter now doesn't mean we don't have to remember energy and kinematics. So the energy at, now let's call, we have a third situation. We'll call this C just after the drop. So between C and A, there's no external forces, right? If we're just talking about just the system is just our ball, then from C to A, there are no external forces going on. So that lets us say that the energy at C should be equal to the energy at A. At C, all of the energy is stored in the height. And at A, all the energy is stored in speed. Mass cancels out. And this is a result we've seen before. The velocity just before impacting the ground is going to be equal to square root of GH. H is 1 and G is 10. So the velocity is just square root of 10. Okay. If the we can also do a similar analysis if we have a point D, which is the height after the bounce, right? So it's the little dotted blue region over here. We can do a very similar analysis and say that the energy at B must equal the energy at D. So we have 1/2 mvb squared, and this should be A. The 1/2 mvb squared will equal mg height at D. Again, masses cancel, and VB equals 2. Man. Apparently I'm still a little slow after going on spring break. So VB is the square root of 2GH. H here is 0.8. So rather than being square root of 20, we have 0.8 times 2 is 1.6 times 10 is 16. So that's just 4. Yep. Very good catch, Addison. All right. So now that we've got, so that's what we can tell from energy. So pre-collision energy conservation is a just fine way to analyze it, as long as we're neglecting air resistance. Post-collision energy is likewise a perfectly fine way to analyze the situation. But to analyze the collision itself, we have to use momentum. So now we would like to say that the impulse that the ground exerts must be equal to the change in momentum, which is going to be momentum B minus momentum A. We're going to keep in mind that momentum is a vector quantity. At A, the ball is going down. I'm going to go ahead and say that down is the negative direction and up is the positive direction. So at A, the ball is going down, so its momentum is negative. At B, the ball is on its way up, so its momentum is positive. So the momentum at B is the velocity at B times the mass. So we have m times 4 minus, and again the momentum at A is negative, so negative m square root of 20. Negative signs cancel. Factor out the m, and we get 4 plus square root of 20. What's the square root of 20? Does anyone know off the top of their head? Okay, Roberto, I believe that you probably knew that, but Josue, there's no way that you knew the square root of 20 to 4 decimal places just off the top of your head. Yeah, but I'm going to say this sum is about 8.8 m. Any questions about this this analysis here? Any questions about this problem? So by the way, if you don't have a way of estimating square roots in your head, um, here's one that usually works. So 20 is between 25 and 16. So we know that square root of 20 has got to be between 4 and 5. 20, though, is 4/9 of the way from 16 to 25. So square root of 20 should be 4/9 of the way between 4 and 5. So square root of 20 is about 4.44. All right, let's look at one more problem. This is an almost good problem. So we are going to alter this a little bit. We don't want to know about the momentum of rain that falls in 1 second. That seems a little nonsensical. Instead, let's ask, what is the average force exerted by rain on the roof of your car? All right. What does it mean when we say there's 1 centimeter of rainfall? I know that we only get like 8 centimeters of rain a year in Nevada, so maybe we're not so used to thinking about what rainfall means. Um, but but yeah, what does it mean if we say that there was a centimeter of rain last night or an inch of rain last night? What does that mean? Yeah, total accumulation. That's right. It means that if you added up, like if you collected all the water that fell from the sky in a certain amount of time, it would cover the ground in a layer, you know, a centimeter thick. So if we're so that's what we mean by a centimeter of rain. If a centimeter of rain is falling in an hour, how much rain is falling per second? So 1 centimeter of rain per hour, and an hour is 3,600 seconds. So we've got something like 2.8 times 10 to the minus 4 centimeters per second. So next question, if that's the depth of rain falling per second, what is the mass of rain falling per second per square meter? So if we had a so if we imagined that I was able to draw three-dimensional images, okay, that's actually not too bad for me. Um, so the total volume of rain we're looking at, so if this side is 1 meter, this side is 1 meter, and the height is 2.8 times 10 to the negative 6 meters, right? Because 10 to the negative 4 centimeters is going to be 10 to the negative 6 meters. So the total volume that we're talking about here is 2.8 times 10 to the minus 6 cubic meters of water. And Addison, you are correct that 1,000 cubic centimeters of water is 1 kilogram. So 1,000 cubic centimeters is 1 liter. But then a cubic meter is significantly more than that. So it's 1,000 kilograms per cubic meter. So if you're doing chemistry, they'll usually quote the density of water as 1 gram per cubic centimeter. But in physics, we don't usually deal with centimeters, so we'll be talking about it in terms of 1,000 kilograms per cubic meter instead. So we have 2.8 times 10 to the minus 3 kilograms of water per second. Let's give ourselves a little room to complete this problem. Also note this is per second per square meter of area. All right, so how does this apply to momentum? Since aren't we talking about momentum today? We are talking about momentum today. So when the water hits the roof of your car, it goes from being 10 meters a second, which is its terminal velocity, goes from 10 meters a second to 0 meters a second. Right? The roof of your car stops the vertical velocity of the rain. So we can write that the impulse exerted on a raindrop is going to be equal to the change in velocity, or change in momentum, rather, between those two times. Now, we've already gone through the trouble of calculating kilograms per second per square meter. So on this side, we're actually going to have the impulse per second per square meter. There's the mass, 2.8 times 10 to the minus 3. And the change in velocity going from negative 10 to 0, that's a change of 10. All right, 2.8 times 10 to the minus 2. So Newton seconds per second per square meter. So let's take a look at these units for a second. See, second, right? So we have a second on top and bottom. The seconds on top is just from the units of momentum. The seconds on bottom comes from the fact that the mass we used was per second. So what unit is newtons per square meter, right? Newtons per square meter is an SI unit. And it's the SI unit of pressure. Which is a Pascal. So there we go. So that's the pressure exerted on the roof of your car during a moderate rainstorm. If we wanted force, then we could just multiply by the area of the roof of your car, but the roof of your car is going to be pretty close to 1 square meter. So that'll give us our desired answer. Any questions? Okay, well, that's all I've got for you for today. So if there's no questions, you are free to go, and